All right, hi everybody. So we're not having a formal lesson today because I wanted to change the schedule a little bit because I have another class that wants to do 8 a.m. on Tuesdays. So um, whether or not you guys can do Tuesday afternoons, we'll talk about that later. But for now, I'm doing a couple of examples for you because I only wanted to do examples for Tuesday's lesson anyway. Um, so I'm starting with a question from the questions by topic on integration in FP3. I'm planning on doing two integrals here, or two questions here. Sorry, which is actually three integrals. And if it takes me only 15 or 20 minutes, I'll probably do a third, but we'll see how it goes. For right now, I'm going to try and do ones that cover all the topics that we've talked about so far. All right. So this first one is June 2011, question 3. We have two integrals here that are in the form 1 over a quadratic or 1 over a square root of a quadratic. And so anytime we have an integral that looks like that, the first step that we want to take is to complete the square of that quadratic. So let's start with the first one. We have, I'll recopy it, so integral from 5 to 8, 1 over x squared minus 10x plus 34. So the very first thing we're going to do is complete the square, which I'm going to do relatively quickly. So that's going to give me integral from 5 to 8, 1 over, let's see, x minus 5 squared plus 9. Right? So you don't have to do it that quick if you don't want. Take as much time as you want when you're completing the square to make sure you get it right. And so this sort of vaguely looks like an arctangent. And so we're going to reference our, for now, since we're not used to it yet, we're going to look at our reference in the notes, which I have not uploaded yet, but I will. We're going to look at our reference in the notes and realize that the thing that we should probably substitute here is x minus 5. And we're going to let x minus 5 equal the square root of whatever the number is, so the square root of 9, so that's 3, times tangent of some other parameter, which we'll call theta. Remember, this is always the tricky step, right? The substitution is the tricky step. Once you have this, everything sort of falls into play, because now we have to find dx and d theta, right? But that's easy, because we can just say, take the derivative of the entire equation with respect to theta. So I'll actually write that out explicitly. Sorry, with respect to x. Or actually with respect to theta. It's a lie. With respect to theta of x minus 5 equals 3 tan. Okay, and if you take the derivative, we end up with dx d theta. Minus 5 goes away. And then we're left with just 3 secant squared of theta. And so that tells us that dx is just 3 secant squared of theta d theta. Right? This is our substitution step. So now we actually have to plug this into our integral. I'll ignore the limits for a second. Our integral is, I'm ignoring the limits, 1 over x minus 5, we called that 3 tan of theta. So we have 3 tan of theta squared. So 3 tan of theta all squared plus 9. And then our dx is 3 secant squared d theta. So we have 3 secant squared d theta. Okay, on the bottom of our integral, we have 1 over 9 tan squared plus 9, and then times 3 secant squared theta d theta. Okay, now 9 tan squared plus 9, that's just 9 secant squared, right, from our identities. So we have 1 over 9 secant squared times 3 secant squared. All right, and look at that. Our secants are going to cancel, and we're left with just the integral of a third d theta, which this is extremely easy, right? This is just a third theta. Okay, plus c, of course. And so if you look at our original substitution, our substitution was x minus 5 is equal to 3 tan of theta. So if I start with that, x minus 5 is equal to 3 tan of theta, I can really easily rearrange and see that x minus 5 over 3 equals tan. And so, of course, theta is just arctan of x minus 5 over 3. And so our integral is in fact just equal to a third of arctan x minus 5 over 3 plus c, which of course we don't care about the c because we're doing it with limits, but I'm just doing it there to have the indefinite integral. And so what we ultimately want is just 1/3 arctan of x minus 5 over 3 from, what was it, from 5 to 8. I believe. Let me just double check. Yes, from 5 to 8. So plugging this in, we get a third times the arctan of 3/8. Right? And then minus the arctan of 0, minus 1/3 arctan of 0. Okay? Arctan of 0 is just 0, so we can ignore that. And so we just have as our answer 1/3 arctan of 3/8. Let's see if they wanted it in a particular form. Something times pi. Let's see. Ah, this would help. It's not over 8, it's over 3. I don't know what I was thinking. Hopefully, about 2 minutes ago when you saw me write that 8 out, you cringed. It's actually over 3. So it's the arctan of 1. A third arctan of 1. And of course the arctan of 1, you can plug this into your calculator if you want, or you can just know it's pi over 4. So you end up with 1/3 times pi over 4, or pi over 12 as our answer, okay? So I'm realizing they have not given me very much space for the second problem, which is okay. What I'm going to do is I'm probably going to erase this one and write the second problem down right where this one is. So just take a minute to look at this. If you want a screenshot or anything like that, it's up here. Alright, so now I'm going to erase it and do the next one, because they've only given me one page of work here, which is annoying, but it's okay. And this is an annoying eraser too. I suppose I could open up a new page, but that would require more work. Alright, let's see. Let's get rid of it. Oh, you guys can fast forward through this part. I wish I could just select an area and delete it all in one fell swoop. But that would make way too much sense. I hope you guys are enjoying this commentary. I know I am. Alright, so for part B, it looks very similar, right? But of course now we're doing it with the square root of the quadratic. So we're going to go through the same motions. We're still going to complete the square of the denominator, right? So I'll still write the integral down. So 5/8, 1 over the square root, x squared minus 10x plus 34 dx. Okay, I'm going to notice, well, I'm not going to notice, I'm going to cheat and say, we've already done part of this. We've already said that this completing of the square is just 1 over the square root of x minus 5 squared plus 9 dx. Okay. Now we have some options here, technically, where we can use tan again, actually, in theory. But if you look at our reference that we had the other day, the thing that makes the most sense here is to use a sinh, right? Because we have cosh squared of t, I was using t's the other day, so I'll use t's here, is equal to 1 plus sinh squared. Right, so it makes the most sense to use sinh. And you'll see why. It's relatively obvious why in a second. So if we use sinh, we would say x minus 5 is equal to 3 sinh. Okay, so a very similar substitution to the one that we did last time. We take the derivative again, so we end up with dx dt, the 5 is going to go away, is equal to 3 cosh. And so dx is just 3 cosh of t dt. Okay. Right, so if we plug this into our integral, I'm going to drop the limits again, so just the integral, I'll write the whole thing out, of 1 over the square root of x minus 5 squared plus 9 dx. This is going to go to, now if we actually plug everything in, integral of 1 over the square root of 3 sinh squared, so I'll write that as 3 sinh of t quantity squared plus 9, this is all under the square root, and then times our dx, but our dx is just 3 cosh. So we have 3 cosh of t dt. Okay, now you can convince yourself, or you can go through the steps in an algebra. I'm not going to go through the steps in the algebra because that's beneath you. To show you that the denominator is just 3 cosh as well. So we end up with 3 cosh of t over 3 cosh of t dt. And so we're integrating just 1. Okay, so it's just the integral of 1 dt, which is of course just t plus c. And then doing a very similar thing to what we did last time, we could say t is just the arc sinh of x minus 5 over 3, not over 8. X minus 5 over 3. And so our indefinite integral, our answer is, so our indefinite integral 1 over the square root of x minus 5 squared plus 9 dx is just equal to the arc sinh, that should be a sinh, arc sinh of x minus 5 over 3, and then technically plus c, but now I'm going to put in the limits again, so from 5 to 8. 5 to 8. So again, we're getting the arc sinh of 1. Arc sinh of 1. And then minus the arc sinh of 0. Arc sinh of 0 is just 0. Okay, so we don't need that one, just the arc sinh of 1. Okay. Right. Do they ask it for a form? They do. They ask it for in the form of natural log of a plus natural square root of n, where a and n are integers. I'll say just plug this in. Right? Plug in. Because I don't really have very much room here to do the simplification. So just plug it in, and you'll get an answer right away. It's very, very easy. Okay. Remember that you have a natural log formula for the arc sinh and the arc cosh and the arc tangent actually as well. So just reference that in your formula book and plug it in, and you're done. Okay, so this is the first one, not too bad. This is a decent summary of what we did, but I want to show you another one that I found earlier. I gotta find it. That's cool, because it's a multi-step problem. This one right here. So this is June 2012, question 7. It's actually a little bit more challenging than, well, not necessarily more challenging, it's a different type of problem, right? But it's going to use a lot of the same techniques. So the first one doesn't have any integrals at all. Obviously you can see that. And let's just get right into it. But we're going to use part A in our integral, right? Actually, I think we're going to use part B as well. And that's kind of the trick in this problem. So we have a function with coshes and sinh. So I'll just write that down. So we have f of x equals 5 cosh minus 4 sinh. Okay. And they ask us to first, before we do anything else, show that it can be written in a different form, which is hopefully going to get us to have an easier form for the integral. So we have, we just want to write it in exponential form, basically, right? Which is fairly easy if we just remember cosh is e to the x plus e to the minus x over 2, and sinh is the exact same thing with a minus sign. So e to the x minus e to the minus x over 2. And so we plug those into our 5 cosh minus 4 sinh. We get 5 times e to the x plus e to the minus x over 2 minus 4 times e to the x minus e to the minus x over 2. We're going to gather the positive e to the x terms, and we're going to gather the negative e to the x terms. Not very surprising here. And we can just basically go ahead and say the answer comes out, right? 1/2 e to the x plus 9 e to the minus x. Done. Really not very interesting. That's part A. All right. So I have skipped some steps here, but they're trivial steps, right? So they're very easy. Go through those if you don't see them. But otherwise, this is good enough. All right. Part B says hence. So hence is a key word here. Solve the equation f of x is equal to 5, and that hence basically tells us don't use the original form, use the part A form, right? So we just want to solve the equation 5 equals 1/2 e to the x plus 9 e to the minus x, like this. So I would start off by multiplying by 2. So we get 10 equals e to the x plus 9 e to the minus x. Now, pause for a second. Try and see if you can figure it out. It's fairly standard. We've done this type of problem a million times. So, good. That's exactly right. So what we do is we multiply the entire thing by e to the x. So we get 10 e to the x equals e to the 2x plus 9. we bring all the terms to one side. So we get 0 equals e to the 2x minus 10 e to the x plus 9. And we say, look at that, we've got a quadratic. This is the same thing as solving the quadratic alpha squared minus 10 alpha plus 9, where alpha is equal to e to the x, right? No surprise here at all. So does this factorize? It does indeed, right? With alpha minus 9, alpha minus 1. Right? Yes. So we get two answers, right? Alpha can either be 9 or alpha can be 1. But these are both equal to e to the x. So we have e to the x is equal to 9, or e to the x is equal to 1. Under the case where it's e to the x is equal to 9, we get that x is equal to the natural log of 9, and when x is equal to 1, when e to the x is equal to 1, we get x is equal to 0. Okay, relatively trivially. And I think they want this in a particular, no, they don't want it in a particular form, right? So that's it. That's part B. Nothing too crazy here. Although you'll notice that in part C, they're actually using this one as well, but they use it as 1/2 natural log of 3. That ends up being a little bit. But you don't actually need that. It's not important here at all. Okay, that's part A and part B. No integration so far, just kind of a review of hyperbolics, how those work. So let's do part C, the actual integral. This is the interesting part, I think. So we have, let's see, we have the integral from 1/2 natural log of 3 up to, I think it was just regular old natural log of 3. Let me double check. Yep. And then it's 1 over the thing that we just used, right? So 1 over 5 cosh x minus 4 sinh of x. And they actually give us the form of the answer, the answer. The answer should be 5 over 18. So we want to show this. So of course, as it's often the case, when they give us an integral like this to do, and in the previous part of the problem, we've taken that function, we've written in a different way, we're going to start off by trying to use that alternate form of the function, right? So we had shown in part A, so I'll say in part A, we showed, obviously you don't have to write all this down, we showed that 5 cosh minus 4 sinh was equal to, what did we say it was? 1/2 e to the x plus 9 e to the minus x. That's all in brackets. And so we're going to insert that into our integral. So we're actually finding the integral from 1/2 natural log of 3 up to natural log of 3 of 1 over 1/2 e to the x plus 9 e to the minus x dx. Now, of course, again, might be a good idea to pause and see if you can figure this one out on your own. I highly, highly recommend it. It's a good integral. And if not, I'm going to continue. So the first thing that I would do is I'd bring the 2 up. I would actually just bring the 2 out of the integral, but who cares, right? So I'll bring the 2 up. I'll say this is the integral 1/2 natural log of 3 to natural log of 3 of 2 over e to the x plus 9 e to the minus x dx. Okay, I would probably make a substitution here as well. I might actually, there's 2 ways that I might go about doing this. I might do a substitution right away, or I might try and do multiply by e to the x over e to the x, and actually in this instance, that's actually what I prefer. So I'm going to multiply this thing by e to the x over e to the x. So I would write this as 1/2 natural log of 3 to natural log of 3 of 2 e to the x over e to the 2x plus 9, okay? Of course, you don't have to do that stuff if you don't want to, but what I've done here, right, so I'll just say, in case you didn't see that, is I multiplied by e to the x over e to the x inside the integral. Okay, once I have it in that form, I'm actually free to do a u substitution, but the substitution that I'm going to make, it might not be 100% obvious, is u equals e to the x. Okay? There's some things you could actually make a slight modification of it to skip some steps here. You could make it equal to 3 e to the x, but I'm actually just going to make it e to the x because it's kind of a little bit easier to see how that substitution, how you can come up with that substitution. And so once I have u is equal to e to the x, I'd say du is equal to du dx is equal to e to the x, of course. And so then solving for dx, we get dx is du over e to the x. And so again, I'm going to drop my limits of integration. We'll bring them back in the end. So I'm going to have my original integral 2e to the x times e to the 2x plus 9 dx. This transforms now with u's into 2e to the x. I'm actually not going to sub my u in there, right? And then over u squared plus 9, and then my dx is going to be du over e to the x, and my e to the x's cancel. Okay? So now I'm actually integrating. I can forget about the original integral for a minute. I'm just integrating 2 over u squared plus 9. Okay? Now I said, and I hope you believe me, that I'm doing probably one or two too many steps. So there's a slightly different u you could use. You could use 3e to the x, and you'd actually already get rid of that 9, and that's okay. But I'm trying to make it so that like it's the easiest thing to sub in, or the easiest substitution to come up with, right? All right. So now this looks awfully like a tangent or an arctangent, right? So what I'm actually going to do now is a further substitution. I'm now going to say let u equal, this is like the same thing that we did in the previous problem, 3 tangent of theta. Okay? That's like using our reference from before. And so du d theta, du d theta is going to be 3 secant squared of theta. If we plug it all into the integral, or I guess we need to actually find du, right? So du is 3 secant squared theta d theta. And so if we plug that into the integral, we get, this becomes the integral of 2 over 3 secant squared, so 9 tangent squared. 9 tan squared of theta plus 9. Okay, and then my du is just 3 secant squared theta d theta. So on the bottom, I get 9 secant squared. On the top, I get 6 secant squared. So this is just the integral of 6 over 9 d theta, or integral of 2/3 d theta. So do the algebra here. I'm skipping algebra. You can do the algebra. I'm confident that you can do that algebra. Okay, and so of course the integral of 2/3, that's very easy. So it's 2/3 theta. So we have 2/3 theta plus c, technically. Right? Now, our theta, if we look at our original definition of u, reversing that gives us theta is equal to the arctan of u over 3. Okay, so we have 2/3 arctan of u over 3 plus c, technically, right? And then if you go to the very beginning, we actually have that u is equal to e to the x, right? So we actually have as our answer 2/3 arctan of e to the x over 3 plus c, okay? As our indefinite integral. And of course, what we want to do is we want to plug in the limits of integration, 1/2 natural log of 3 up to natural log of 3, which again, you do this, okay? That's just a matter of knowing how to use natural logs. I'm reasonably confident that you guys know how to do that. Maybe that's a silly thing to do. No, I'm just kidding. Right, so these are two good problems from the questions by topic. I don't want to do too many because I want you to have more for yourself. But actually, as a matter of fact, just scanning through up until this point, these are the only two that you're actually really fully equipped to do. Actually, you could do this one. So this is a good one for you to try. So this is June 2012, question 5. That's a very good one for you to try. You can't do this one yet. Can't do this one yet. Can't do that one yet. Yeah. Cannot do that one yet either. And can't do that one. But you can do this one, so try this one. So that's June 2010, question 2. Do that one. And this one you can't do. This one you can't do either. That's it. All right. So, and there's, of course, there are more plenty more exercises to choose from. But I thought this would be a nice little quick recap. Hopefully, Javier, the video's not too long for you. I remember that it was very difficult for you to get through my 30-minute videos last time. I think I'm right under 25 minutes. I'm going to stop before it gets any longer. All right. I will talk to you guys on Wednesday, and I hope D1 goes or went well, depending on what time you watch this. All right. Talk to you guys later.